Welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but still want to be its friend.
I'm Connie, your curious co-host.
And I am your other co-host. I'm Dr. Moiya McTier. I'm an astrophysicist, a folklorist, and a friend to all of the beings and entities who are currently a part of this call. It's the last episode of the year.
Woo.
The smallest woo I've ever heard.
It's literally just the smallest woo. It's not a big one because, well, the stuff. Whatever that means to you.
Yeah.
Whatever that means to you.
Well, let's take a moment, Bestie, to reflect on this past year.
Okay.
Let's each do a rose and a thorn.
Okay.
What's a good thing that happened to you this year, which I would like to hear second, and before that, I would like to hear the thorn, which is what kind of stung you this year?
Yeah. I mean, I think there are probably plenty of people who can agree that, like, the world, the economy, the everything having to do with, like, politics and geopolitical engagement was a pretty big thorn. And it's sometimes just in the ways that it affects you personally, in addition to just the horrors. And so, you know, it took me a really long time to get a job, a consistent job. And it's still not where, I was before, but I know that the stuff, the horrors, have seriously impacted me in that way. And so I forget what the number was of, like, Black women who have been, removed from their corporate or government jobs. And so I was among that number. And yeah, that was, it happened last year, but, the effects have lasted all through the year. So that's mine.
Mm-hmm. And your rose?
Yes. Despite all of that, I made a pretty big move this year, literally cross country, like doing so many things I've never done before, finding myself, which is still, she ain't found all the way, but we're getting there. And so I'm in a better place than I was at this time last year. Like, I feel better. And so that's my rose. How about you, my friend?
Oh, the world is trash and I hate it here.
Yeah.
But I'd say my thorn of the year is that my dad died. That sucked.
Yeah.
And my rose is that I finished a book and I got to dedicate it to him, which was really nice.
Incredible.
Because I know that my mom read the, early drafts of chapters that I had to him when he was in the hospital. And I really wanted him to see the book, but he won't.
Yeah.
But, the book is for him anyway.
Mm-hmm. Absolutely. The rose comes with a thorn.
Yes. It's a beautifully spiky plant.
Mm-hmm.
Not my favorite. I don't like getting roses. I don't. It's cliche.
Yeah,
put a little more thought into it, please.
Yeah. I'm into that. I think roses are, they're fine. But if you can get creative, get creative. Mm-hmm. Mm-hmm. But they're fine. I'm not like
fine.
Love. But they are very fragrant, and that's nice. But then they just kind of wither on me.
as flowers are wont to do.
As flowers do. Mm-hmm. Yeah.
As the universe perhaps will eventually do.
It's like I don't even have questions. I just have gaping feels of
really?
Like, it just feels like I think I said this before, but it feels like the THX sound at the beginning of movies, just like when I think about our topic for today.
Okay, so listeners, today we're talking about the end of the universe. It's the last episode of the year, so we're going to talk about the last things that will be here when the universe ends. And I don't understand why it would bother you. Can you please tell me why?
I don't know. It just feels really big, and it sounds, it's silly to say, but it sounds permanent in a way that's just like daunting. Just like,
okay.
Over? Like it's the over part that I can't really comprehend, and what that looks like, which we will, I'm sure, get into, of like what will be left
and what it'll look like. Yeah,
but I don't know. Just it's such a big literally cosmic thought in my head that I'm just like, I don't even know how you would begin to think about it.
Does it give you some sort of existential dread to think of the concept of pure nothingness?
I think it does.
Wow, that sounds like the ultimate bliss to me.
Of course.
Like I cannot wrap my mind around any discomfort with ultimate oblivion. Wow.
Yeah.
Ugh, one day. One day. Well, let's run down the different fates. Since you don't I think instead of starting with questions, maybe let's just dive into big picture possibilities.
Okay.
Because this is still an open question. We don't know exactly how the universe is going to end. That's why the science is ongoing, and we still need to, do our observations, take our measurements. But from what we currently understand about the universe, it seems like its ultimate fate depends on the behavior, long term, of dark energy.
Oh.
Bestie, what do you know about dark energy?
I feel like it's come up and it's different than dark matter.
Yes.
And it's more about negative space.
Yeah.
Or is dark matter the negative? No, because dark matter is still
matter
and tangible in some way.
The jury's still out on whether or not you could touch dark matter because we think that it might not be interacting through that force. We touch things through the electromagnetic force. It does not interact with the electromagnetic force. That's why it's dark. It's invisible.
Okay.
And dark energy is something completely different. You were right about that, Bestie. And it does have to do with the emptiness of space. So, no one knows much about dark energy, actually. So that was a bit of a trick question because we don't know what it is or how it works.
Right.
We have only coined this term, dark energy, to give a name to this ununderstood. I feel like the opposite of understood should be overstood, but that would mean understood.
Yeah. Yeah, it's one of those words where if you try to flip it, it kind of still means the same thing. That's fascinating.
Yeah. Well, whatever word I'm looking for, this mysterious, unidentified force that is not just making the universe expand, but making the universe expand at an ever faster rate. We learned in the 90s that the universe is accelerating in its expansion. So right now, at this moment, I'm going to make up a number, but at this moment, it's moving at 50,000 miles per second. And tomorrow, it'll be moving at 55,000 miles per second because it's getting faster all the time.
Right. Okay.
Those aren't real numbers.
Right. Huh.
Yeah. And so dark energy could be a consequence of emptiness, so that if you have more empty space, dark energy gets stronger. Just like if you have more mass in a concentrated space, gravity gets stronger. So dark energy could be the antithesis of gravity, or dark energy could be a constant that is throughout the universe, so it won't get stronger over time as the universe expands. So those are the two big possibilities. We're not sure which one it is. We have come up with different scenarios for the end of the universe, depending on the different strengths of dark energy. So I have here those different possibilities from weakest dark energy to strongest dark energy.
Okay.
Because it can be either a constant or it can be a variable number. And so, but I'm still just saying relative to whatever the other forces are, weak versus strong. Even if dark energy is a constant, maybe it's always weaker than gravity, maybe it's always stronger. Or if dark energy varies, then it can still be weaker all the time, even if it, we just don't.
Yes.
I'm not explaining this well, but
that's what I was trying to understand. Yeah, there's a line where gravity is, and then it could be that it moves underneath it or it crosses. So that's or it escalates and it crosses the boundary of where gravity is, and it could increase above gravity. It could be weaker than gravity now, but at some point it could be equal and then and then greater?
Yes, this is the point of the different scenarios. So let's go through them.
Yeah.
If dark energy is really weak, as the universe expands, gravity will eventually overcome it. So its expansion will slow down as all of the material in the universe uses its gravity to pull back on the edge of the universe. So in that scenario, the universe expands until it slows down and stops, and then it contracts back in on itself until we go back to the primeval atom where the Big Bang started. So it's we call this the Big Crunch because the universe is like crunching back in on itself. That's if dark energy is really weak. That's if we have what we call a closed universe, where the shape of the universe is more like a ball or a sphere where it's curving in on itself than a flat plane.
Okay.
The next scenario for dark energy is very similar. The universe expands, but the acceleration slows down until it stops, and then the universe contracts back in on itself. But when it reaches that primeval atom state, there's enough energy in the system, not necessarily dark energy, but just like generally there is enough energy in the system that it bounces back out, causing another Big Bang. This is the Big Bounce hypothesis, where the universe is in a constant oscillatory state of expanding and then contracting and expanding and contracting. So in this scenario, what happened before the Big Bang was actually just another universe that experienced its own Big Bang and expansion and contraction. And our universe that we exist in will be the pre-universe to whatever universe comes next.
It's giving multiverse. It's giving this is
No, because
no,
multiverse is many universes at the same time.
Yes. Okay, yeah. I guess in my head it's more like they don't have to be linear.
This is sequential universes. Big bounce. Many iterations of the universe in order. If dark energy is a little bit stronger, if it has an intermediate strength so that it isn't like obviously going to lose to gravity or overcome it, then the universe will continue to expand forever. And like maybe continue accelerating or maybe just plateau at a certain point, but it won't succumb to gravity and contract back in on itself. We call this the big freeze or the heat death of the universe.
Oh, okay.
This is a scenario where the universe is more of that flat shape. And we think that this is probably the most likely scenario. But we still have a lot more to learn about dark energy before we can say for sure. But that is what I'm going to talk about for the rest of the episode. After I explain the final scenario, the final scenario that relates to dark energy anyway. This is if dark energy is super strong and it will overcome gravity and the universe continues to accelerate its expansion forever. Eventually, the universe will rip itself apart. So we call this the big rip. Even in like the big freeze scenario, if the universe continues to expand, our galaxy will stay together because the gravity of our galaxy will be stronger even than like the late term dark energy strength.
Okay.
But in the big rip scenario, all of the space becomes filled with dark energy and even individual atoms get ripped apart eventually.
Oh, so this is not like a separation of things in the universe. It's more like the tinier level.
Well, it is a separation of everything in the universe.
Okay. But I mean, is it more like a pulverization situation or more like a you stretch it and there's like gaps in between and there's like little pockets of planets and
everything gets stretched. So what's currently happening is that galaxies are being taken away from us at the edge of the universe by dark energy. If the big rip happens, the stars in those galaxies will be pulled apart from each other. So the galaxies get ripped apart. But then the planets around those stars will get pulled apart from the stars. So the solar systems will get ripped up. The planets themselves, the molecules that make them up, the space between them will be expanded by dark energy. And then within those molecules, the space between the quarks that make up atoms will expand so that on the atomic level, everything is ripped apart.
Well then, the great R.I.P.
Yes. R.I.P. to all of the
Everything.
all of the material in the universe. But we think that's probably not going to happen. We think that the big freeze or the heat death is the most likely scenario. And so all of the kind of long-term timelines of the universe follow the timeline of the heat death. Heat death is a logical consequence of thermodynamics. This is a field of science that was started in the 1800s. Lord Kelvin, whose real name was William Thomson, not Kelvin at all. That was just like his title.
Right. That always confuses me.
Yeah. He gave his name to the Kelvin temperature scale.
Yeah.
And that's because he spent a lot of time thinking about heat and the dissipation of it and how it relates to energy in the 1850s. And then other people took up this idea and applied it to the universe once we realized, or once we were better capable of measuring the temperature of the universe and its size and its shape and everything. So we're talking 1900s. And so after all of that, it seems that according to the heat death, the universe could last. There's not even a number for it. 10 to the thousands, millions of power of years.
Okay. Wow.
The shortest estimate for the age of the universe in the heat death is 10 to the 100th power. So when people really, you don't be worried about the end of the universe. If anything, be what's taking you so long?
True.
It's have you ever been in a movie and you're like, oh, I just want this to be over already? There's just trim the fat.
Right.
We don't need all this. There's too much exposition.
We're in the story. We're in the center.
Well, I mean, if the universe truly is going to last, way more than a Googleplex years, we are at the very beginning. The universe is a baby.
You're so right.
And so I thought it'd be nice to think about what the universe will look like as an old, and what will be left, and what will it look like? Spoiler alert: it won't look like anything, because by the end of the universe, light won't exist in a way that we could actually perceive.
I didn't know it was going to somehow feel worse than the Great Rip, but somehow the Great Freeze is wait, okay, we're just separating, and you're no, you won't be able to comprehend it anymore.
Yeah.
Okay, great. That's great for my brain ahead.
Cool. Okay, so let's start talking about some things ending.
Yes, tell me about the geriatric universe. So
we are currently in an age of the universe, an era or an epoch that we call the radiation-dominated era.
Okay.
Radiation is like photons. It's electromagnetic radiation. It's cosmic rays. It's neutrinos. It's this really high-energy, small particles that zip through the universe and carry a lot of energy with them. So there's a lot of that right now. We are in the radiation-dominated era. You can also, there are other eras that are, they don't have that light. And maybe they were more dominated by energy. That was the very early universe. We're going to talk about that next week.
Okay.
And then you can have matter-dominant eras, which will come later, where there's still material, but not necessarily a lot of light. Also early in the universe, where there was material, but not necessarily a lot of light. Yeah.
Okay.
So right now, we are about 13.8 billion years into the universe. It's just 13.8. It's just 13.8.
Just with a B. Just is fine.
But it's just,
The B stands for bands.
It's almost 14. Yeah, we're almost 14 bands into the universe. And our sun is about 4.5 bands old.
Okay.
Now, in about 5 bands, the sun is going to have finished fusing most of the hydrogen just in its core. But actually, stars aren't very efficient at hydrogen fusion. Little known fact.
Okay.
So a star like our sun is probably only going to fuse about 10% of its hydrogen into helium over its lifetime.
Okay.
But once it runs out in its core, because when the star starts, it's all hydrogen, and then the core is what fuses. it will run out in about 5 bands.
Okay.
It will move off of the main sequence, which is like this chart that astronomers have for graphing stellar evolution. And it will enter the next phase of its life, where it will puff up into a red giant and start sloughing off a bunch of material in its outer layers, and then eventually lose enough material that what's left behind is a core that we call a white dwarf. And it's not fusing hydrogen anymore, and it's not that bright, and it's not, I guess it's pretty hot, but it's like a stellar remnant at that point. We don't call it a star. So that's in about 5 bands, 5 billion years.
Wow.
All of that, stars fusing in their cores and then exploding, the massive ones like the O-type stars, they explode and they release the heavy elements that they produced out into the interstellar medium, is what we call it, the space between stars. And then that material gets gathered up in the next generation of stars that now have heavier elements in them. That cycle is going to continue for another 10 to the 14 power years. That's about 100 trillion years.
Okay.
So this era where the universe is kind of actively forming stars by collapsing clouds of gas, we call that, and I think this will be a new vocab word for you, bestie, the stelliferous era. It lasts from about 100 million years to about 100 trillion years. After that point, the universe will have used up pretty much all of its gas, and it can't make any new stars in that same way. So the only stars left will be the really low mass M dwarf stars. Each of those can live for trillions of years. The universe actually isn't old enough for us to have seen an M-type star move to the next evolutionary stage. So we don't really know what's going to happen or how long it's going to take, but we do know that they will be the last stars left over.
And we know that because it's going to continue to let off.
These low mass stars, they are very efficient in their fusion, so they will just spend trillions of years slowly fusing hydrogen in their cores. The cool thing about these low-mass M-dwarf stars is that they are fully convective, so their entire layer is actually kind of like a boiling pot of water, just constantly churning material from the top layer to the core inside. So it's really efficient at like transporting material, so all of it mixes together and can be fused. As opposed to stars like our sun, which have not fully convective bodies. They have some radiative zones where the heat has to transfer through just like radiation moving through the space instead of convection where there's physical contact between molecules of different temperatures. I was not planning on going into this, but you looked interested.
Yeah, because instead of letting something off, it's more like what's left is like cooking itself, and then it will use up all of it. There will be nothing left over. And so then that's what will be left.
Yeah, it's like the M dwarfs are slow roasting.
Okay. Yeah. Okay. And then it will just, is it burn out or not? The terminology there.
Not burn out because they're not on fire. But,
right.
We don't know exactly what's going to happen to these M-type stars. Maybe they will become white dwarfs. Maybe they'll become something else. Maybe they'll become black dwarfs, like just cold chunks of rock in space that don't give off any heat. I'm not totally sure. But they will be the final stars, and they'll last for trillions of years. Scientists have defined the final mass function, so the distribution of masses of objects at the end of the universe. And about half of the objects left over will be white dwarfs by mass. About half of the entire mass of the universe will be wrapped up in white dwarfs. The rest will mostly be neutron stars and black holes with some, planets. There might be some planets that haven't been absorbed into their stars yet. Hey friends, it's me. Connie is playing around with my shrink machine that I keep in the corner of the office so that she can see all of these tiny particles we're talking about on their own size scales. So I figured I'd take the time to share some messages with you. The first message is a big thank you to all of the patrons who support Pale Blue Pod financially every single month. This is an independent podcast and we rely on listener support like yours to keep going. So thank you so much. And I want to give a special shout out to our Sun-like stars, Scott Reynolds, Tom T., Nicole Bartlett, Ashley Shambo, Mark Mahoney, and Bruce Sedloff. Thank you, thank you, thank you, my golden friends. If you would like to support this indie podcast on Patreon, hear your name on the show, make it onto the patron star chart, and get research notes for pretty much every episode, you can do that for $5 a month at patreon.com/palebluepod. That link is also in the episode description, as is a link to our PayPal, where you can make a one-time donation and become a supernova in the Pale Blue Pod sky. That's if a monthly subscription donation isn't for you. Of course, if you can't support the show financially right now, we totally understand and we love you because you are still space. The best way to help Pale Blue Pod grow is actually to get more people listening to it. So please take a link to this episode and send it to someone who's always been curious about how the universe might end. That way, you're helping them become closer to the universe and you're helping Pale Blue Pod. So thank you in advance. My next message is a podcast recommendation. It's a show from Multitude called Simple and Clean. This is a show where the hosts, Misha Stanton, who edits Pale Blue Pod, and Mayana Barron, one of my favorite recurring guests, actually, I think she came on 2 or 3 times. They talk about Kingdom Hearts, which is a little video game franchise about really big feelings. I've never played it, but hearing them talk about it makes me feel, like I have almost. If you've never heard of Kingdom Hearts, that's okay. They are here to break it down for you and explain why they love it, and hopefully to convince you that this weird little story deserves a place in your heart. Each week, Misha and Mayana will attempt to unravel how this deceptively expansive game series has touched an entire generation of deeply earnest weirdos. And along the way, they'll realize what they were talking about might not be just a video game, but a whole lot more. New episodes come out every Sunday wherever you listen to your podcasts, so check out Simple and Clean. All right, Connie has come back to the macro scale, so let's keep talking about the last stars. And remember, friends, none of this stuff is happening for 1 trillion years, so none of it really matters. But it is interesting to talk about. So that's going to about 100 trillion years. At about 1 trillion years, so while all that is happening, while stars are still forming, have we talked about the cosmic microwave background, bestie?
It sounds familiar, but I don't remember why.
Okay. I know I've talked about it on the show before, but it must have been before you joined. The cosmic microwave background is essentially the heat signature left over from the Big Bang. It shows us how matter was distributed very early on in the universe when the electrons first bound to the atomic nuclei. So the cosmic microwave background is this signal that we can see all over the universe. And after about 1 trillion years, the cosmic microwave background, the waves of light that carry it, will have been redshifted. They will have been expanded as the universe expands to longer and longer wavelengths, so long that we cannot observe them. Because early on in the universe, when that light was initially emitted, it was in the X-ray or something, maybe the ultraviolet, which we just covered. But as the universe stretches, so too do those light waves. And so it gets longer wavelengths. Now it's in the microwave. Eventually it will be in the radio, and then we won't be able to see it at all after about 1 trillion years. So we won't have any evidence of the Big Bang. And this is before stars stop forming. So this is only at 1 trillion years. You need a second, bestie?
Yeah.
Okay. What's going through your mind?
Yeah. So I'm thinking about the colors, and I got stuck on the fact that the things that are the different wavelengths, they all kind of shift.
Not all.
Okay.
So this is light that has been traveling through the universe for billions of years. And I mean, those photons are a part of the universe And so as the universe gets expanded, they also get expanded. But not all photons that are coming to us travel far enough or long enough to experience the expansion.
Okay.
This is just really old light.
This is just old light. It's not all of the light.
Correct.
Okay.
Correct.
Okay.
But this whole phenomenon, this red shifting of light, you've heard of the Doppler effect.
Right. Yeah.
Yeah, where things can be blue shifted or red shifted. That happens because the object that's emitting the wave is moving towards you for blue shifting or away from you for red shifting.
Right.
The way we figured out that the universe is expanding and accelerating in that expansion is that we studied the light from galaxies really far away from us, and we noticed that the distant galaxies were more red shifted. Wow. So they were moving away from us faster than the close galaxies. So things that are far enough away, if their light has been traveling far and long enough, then it will experience this stretching.
Wow. Okay.
But, only the really, really far stuff.
Okay. That helped. Good. Thank you, bestie.
You're welcome.
Before she makes it worse.
I know. Because remember when I told you that stars form from collapsing clouds of gas? Yeah, well, it will only do that for 100 trillion years. After that, from about a quadrillion years to whatever 10 to the 23 power is. Now we're getting past where I know the word, so I just have to use the exponents. I'm so sorry, bestie.
Oh, no.
But from 10 to the 15 years, which is, I think, a quadrillion, to 10 to the 23 years, we have this new mode of star formation, where instead of forming from collapsing clouds of gas, stars form from smaller objects like giant gas planets or brown dwarfs, which are almost massive enough to be stars. They collide and form new stars. So that's going to happen.
Okay.
After,
is this with the heavier elements that you were talking about?
Well, not just the heavier elements. I mean, all of the heavier elements will have been in the last bits of gas that get pushed into the last stars. These are smaller, we call them substellar objects. These are big balls of gas that weren't quite massive enough to be fusing hydrogen into helium. So I think we've talked about hot Jupiters and how, the most massive Jupiters can be, almost as small and almost as hot as the smallest stars. Yeah. So it's like that. If you get those types of objects colliding together, their gas will mix and it will set off chemical and physical reactions that can ignite fusion and create new stars. But it's going to be really hard to do because you have to get these things physically smashing together in a universe that is
already expanding.
But not on the scale of galaxies. So things within galaxies are still gravitationally bound. This is the beginning of what scientists call the degenerate era of the universe.
This entire time I've been like, it does conveniently kind of match up with the progression of a person. Okay, in its early years and then in its teenage years, it lets its old light go. And then you said around 10 to the 23rd years, it goes through its degenerate era.
Well, at 10 to the 15 years, it enters the degenerate era.
Okay, that tracks.
And this, we still have light. The cosmic microwave background is a very specific type of light. Stars will still shine, and there will still be brightness in the universe.
Yeah, in this analogy, it's more like puberty's over. You've hit puberty, and so your childhood has gone away.
So here, the CMB represents one's childlike innocence and wonder.
Exactly.
Interesting.
And then they enter their degenerate years.
Yeah, the degenerate years. So it's called the degenerate era because most of the matter here at this point is dominated by degenerate matter, like neutron stars. Neutron stars are the second densest objects in the universe. They can be the size of cities, but the mass of a sun. The mass of a sun, you condense it to the size of New York.
Oh, wow.
That's a neutron star. They are so densely packed, they're atoms are really, really close to each other. So their electrons like don't have any space to move. I think under some circumstances, their electrons are actually sharing energy shells with their neighboring atoms' electrons. And so it's called degenerate because the atoms can't move. And if they were to move, then they would be in the same physical space as another. So it's that kind of degeneracy. It's when you like when you say a degenerate statement that's like, it's almost like redundant. Like you did, like we knew this. These two things are saying similar things.
Wow. Huh.
So in this physical context, these two atoms or these two particles are in the same space. So they are degenerate.
Okay.
And that era lasts a very long time. After that, or I guess while that's happening, at about 10 to the 19 years, stellar orbits around galaxies will start to decay. So the stars that are close to the center, they'll like swirl into the center and fall into the black hole. They will also start to evaporate. So the stars that are on the outside of galaxies, they will kind of like just float away from the galaxy over time.
Where are they going? We don't know yet.
Just carried away. Just carried away by their motion.
Like a little dandelion. Just like,
wait, bye.
Goodbye.
So those are the ones that aren't, gravitationally bound as tightly to the galaxy. So dark energy might be able to carry them away. So the next thing that starts to happen, and we're not totally sure that this is possible, but the next time scale that becomes important is on the order of 10 to the 34th power years. That's the time scale where protons, which are extremely stable particles, they're made up of quarks, of 3 different types of quarks. I think we talked about this in one of our episodes.
And I want to remember which... It's like directions or something. Like it's something, the 3 different kinds. It's something
6
a little
different
funny.
Kinds.
Oh, yeah. 6.
Yes, up, down, strange, charm, top, and bottom. And a proton, I'm fairly certain.
So good though.
A proton is 2 ups and a down, and a neutron is 2 downs and an up quark.
Okay.
And because of the masses of different types of quarks, protons are a little bit more stable. Protons are a lot more stable than neutrons, and it takes them a very long time to decay. We've never observed a proton decaying, not even in the particle accelerator experiments that we do at CERN. But hypothetically, if they were to decay, they would fall apart into even smaller particles. They would produce neutrinos or pions, which is like a special type of energetic particle, like a high energy type of thing. A pion is made up of a quark and an antiquark. So like the proton is just splitting up into smaller pieces, but it will only do that after at least 10 to the 34th power years.
Right.
So that'll take a long time, but protons and these particles will probably be the last things left in the universe after everything else happens, just because like protons are everywhere and they take this long to decay into other stuff. Well, actually, I guess it's the other stuff that will be the last things, those neutrinos and the pions. But that's 10 to the 34 years. We're in this degenerate era. We have all of these neutron stars and white dwarf stars. They need to radiate away all of their energy, and that takes a long time. That takes about 10 to the 68 power years.
Okay, now is this all happening on the like micro submicroscopic level?
No, I mean not these stellar remnants radiating away their energy. Okay, so there's still
big objects.
Yeah.
In the physical plane. Just lots of interesting stuff is happening on the atomic level.
I mean, no more than the stuff that's happening on the atomic level now.
I'm just trying to see, understand what might be visually different.
At this point,
yeah.
Nothing.
Really? Okay.
Well, at this point, right, like you can't see the cosmic microwave background.
Yeah.
Our sun is gone.
Yeah,
But
like-
there are still stars that
Yeah.
shine, but most of the high mass stars by this point are gone.
So much
like,
fewer. So it's like lights going out.
yes.
Okay. Okay.
Yes, and those massive stars, after they are gone, they are leaving behind these neutron stars, and solar mass stars are leaving behind the white dwarfs, and they need to radiate away all of their energy, but they are still big chunks of material out in space.
Okay.
They just then become cold chunks of material, and when they're cold and they have like no energy left anymore, to a scientist, they're dead. They're done.
Gotcha.
But we'll talk about it later because there's stuff that can happen. Okay, so after the 10 to the 68th power years, when the neutron stars and the white dwarfs have radiated away all of their energy, now the universe is cold. Like there's some heat from low mass stars, but a lot of it has been radiated away. Now we have to deal with the black hole era, where there's really not much light and there's not much heat. So black holes, we say that they are, gravity wells and that nothing can escape them, not even light. That is true. But in 1975, Stephen Hawking published a paper called Particle Creation by Black Holes, where he proposed that there is, and we call it Hawking radiation because, he's so clever and, not egotistical at all. He proposed that this type of Hawking radiation can slowly evaporate away a black hole over time. And the more massive a black hole is, the longer it's going to take, obviously, because there's more material. But for a black hole the size of the supermassive black hole that will form when the Milky Way and Andromeda collide. So at that point, it would be, maybe 10 million times the mass of our sun. That would evaporate away through Hawking radiation in 10 to the 90th power years. And that is a relatively small supermassive black hole. We've seen supermassive black holes that are up to tens of billions times the mass of our sun. So that would take a very, very long time to evaporate away.
Wow.
Would you like to know how this Hawking radiation works? How can black holes lose energy?
Yeah, because I don't understand the evaporate. Evaporate is what does that mean?
I mean, it means exactly what it says. Evaporation is the process of material getting more energy so that slowly over time, small particles dissipate at the edges of it, at the boundaries. They evaporate away at the boundaries. And that's what's going to happen to black holes. So we have to go back to quantum field theory to understand this. And quantum field theory basically says that all particles that we talk about are spikes in a fluctuating energy field that exists everywhere. Like how if you're standing in a field here on Earth, the ground exists everywhere. Blades of grass are spikes in that field. You would say, you can see individual blades of grass. You can see all of the blades of grass moving in the wind together, just like you can see fields of electrons working together, or you can see individual electrons.
Okay.
Yeah, so every elementary particle that we talk about, an electron, a quark, a Higgs boson, we talked about the Higgs boson once, those are all spikes in their respective quantum energy fields. And because these quantum fields are constantly fluctuating, you can have a spike that just randomly appears somewhere. And the spike isn't a particle that physically moved into that space, but it just popped into existence there, appeared randomly. Quantum theory says that particles can just appear. They can just pop into existence randomly in space. Except when that happens, usually what appears is a matter particle and its antimatter counterpart. Every particle has an antimatter counterpart. And when you get them together close enough, they will completely annihilate each other. So usually we can't even notice it. If a quantum particle just pops up, it will annihilate with its antiparticle counterpart immediately.
So it pops up and then disappears again?
Disappears. Yeah. The two of them, they'll pop up like arch nemesis in the night, and they'll do
Battle
a
each
quantum
other.
fight,
Yeah.
and they'll both die.
Right. Okay.
And so normally that means like it takes energy for them to pop into existence, but then when they annihilate, that energy just goes right back to the environment. If you get those two particles popping into existence right at the edge of a black hole, then one of them might fall into the black hole and not be annihilated. So you end up with one that falls into the black hole and one that can move away because it's like technically outside the event horizon. And then you've used energy from this system to create the particles, but the energy didn't return because the particles weren't annihilated. So it's a tiny fraction. Stephen Hawking like calculated it out. It's teeny tiny, but over time, you could actually just like evaporate enough energy away from the black hole for it to not exist anymore. The ultimate ashes to ashes, dust to dust.
That is truly brain wrinkling. And it's one of those things that feels like how do we, I guess we don't know this, right? But it's like,
We don't, exactly.
But it feels like I don't want to say it sounds like science fiction, but it's like, let's just, it's like a head canon. Like, I wonder what will happen at the end of the universe.
It's a thought experiment. That is what a lot of theoretical physics is.
Okay, because I don't know that much about it. And so that is interesting. Okay.
Yeah, we have not observed this. We haven't been able to see it out in space or try and recreate these conditions in a lab. So
right.
It's completely hypothetical.
Yeah, because that's where I was like, have we calculated something? Like some of the things I know are like we know the sun will do X, Y, and Z because of the particles within it and how they interact. And so you can calculate like what the potentialities are.
We can calculate this, but we cannot measure it. There are no observable quantities that we can. It would be a lot easier to observe around a low-mass black hole because it would happen more frequently because a low-mass black hole has a weaker gravitational field, so it'll be easier for the remaining particle to escape, but we still haven't observed it. Wow. So since we can't observe it, we can't measure it.
Right.
But we can still run calculations based on models and hypotheses.
Wow.
Stephen Hawking and I had the same birthday.
Capricorn.
Not same year, obviously. Definitely not my favorite person I share my birthday with.
Yeah.
Like, far from it. Yeah. It's David Bowie.
Ooh.
Bisexual icon, David Bowie. And I, other bisexual icon, Moiya McTier, share a birthday.
That's great, because for your birthday post, I used a David Bowie song as the background to it. Yes. Space Oddity.
Bestie.
Because you are.
I love that so much.
Yes.
Because I am a space oddity.
Yeah.
My favorite David Bowie song is actually Dance Magic Dance from the Labyrinth movie soundtrack.
Of course. Of course. I've
Slap
known
that
this.
baby, make him free.
You know, I've seen Labyrinth with Moiya, and I'm still like, wow.
I make all my friends watch it.
It was a good time.
It's required viewing.
It was a good time.
Back to serious science, Moiya.
Yes, the geriatric end of the universe.
Yeah, because we are at in the last things of the universe. The black holes will be last. They'll evaporate away eventually, and then we'll just have like some energetic particles floating through space. There will still be photons that zip around, but their wavelengths as they travel through the expanding universe will be stretched so much that we can't see them. If protons do not decay, because we've never seen one decaying into a smaller particle, then after 10 to the 1500th power years.
Oh, no.
1,500. That is how long it will take all of the cold chunks that are left in space. So all of the stellar remnants, all of the planets, all of just like the physical material left over, they will eventually fuse through a process called muon fusion.
Okay.
I'm not sure exactly how it works. A muon is a fundamental particle. It's kind of like an electron, but it's a little bit heavier, but it carries that charge, and it's not made of quarks or anything. So muon fusion will take all of this material, squish it together all into iron. Like, it will collapse all of the atoms into each other to make iron atoms. So we will have then, after 10 to the 1,500 years, just a bunch of iron stars. And then those iron stars could eventually collapse into black holes through a process called quantum tunneling, where, because quantum processes are just kind of like weird and anything can happen at any moment, occasionally you can have a fundamental particle like an electron that seems to teleport through a material, and we've timed it, and it takes them less time to appear on the other side than it would to travel through the material.
So this is something we have observed.
Yes, we have observed quantum tunneling.
Okay.
We know that that is true, but we have never observed quantum tunneling make a black hole from an iron star. That will take a very long time. But then we'll have new black holes that can evaporate through their own Hawking radiation. So then the universe gets another kickstart. That is called the dark era of the universe, where all of the light from the stars has gone out. And because the photon wavelengths have been stretched so much, we wouldn't be able to see anything. So that's the dark era. So then there is no more physical chunk of stuff left in the universe. It's all just broken down into its component fundamental particles. Yeah, after 10 to the 1,500th power years.
Right.
Bestie, I'm about to make you feel better, I think.
Okay.
So that would be the end of the universe in the heat death of the universe, except for weird quantum phenomena. So some of my favorite mythologies are ones that have a cyclical understanding of the cosmos, ones where their apocalypse story is actually just a new beginning. And so I found a scientific basis for how that might be the case.
Okay.
Quantum stuff is weird. Random things can happen. A particle can teleport to a new space. A new particle can appear in a space where there was nothing before. And so given enough time, the estimates say 10 to the 56. So whatever that number, that's now the exponent. So we're taking 10 to the 10 to the 56th power. After that many years, I don't even know what the number for that would be. I have no clue. After that many years, a random quantum fluctuation could conceivably kickstart a new Big Bang, because we still have all of the constituent material.
Right.
So if you get a process that can kickstart just some like energetic thing, it could conceivably set off a new universe.
The butterfly effect, but on the cosmic level.
Yeah. Yeah.
Okay, so just to be clear, it is 10 in regular script, and then 10 to the 56 is in superscript.
Correct. So 56 is superscript.
Oh, it's like Inception?
Yeah,
Like
Inception. So the number is 10, and then that exponent is 1 followed by 56 zeros.
That's
yeah, just the exponent alone is 10 to the 56th power. But we'll all be dead by then anyway, so we don't have to do the waiting. Actually, that's so long that at some point in there, a Boltzmann brain might form. So they might be aware of the time it takes, but we won't.
A what?
A Boltzmann brain is a kind of like joking, hypothetical consequence of the random fluctuations in the universe, where given enough time, because particles can just appear, perhaps you will get a random assortment of particles that arrange themselves in a way that perfectly mimics a human brain with its own memories and consciousness. There was this joking thought experiment from back in the, 80s or something, 70s. Heinrich Boltzmann, Friedrich Boltzmann, some scientist
Some
who
guy.
probably had a German-sounding first name. His colleagues were kind of making fun of him for his ideas about these random fluctuations in the universe. And they were like, well, if you take it to the extreme, then eventually a human brain can form. And how do you know that we are not just one of those Boltzmann brains experiencing, quote-unquote experiencing, but actually the universe has just popped us into existence with all of these memories and perceptions.
Oh, trippy.
And so given enough time before the Big Bang would happen again, you would get a Boltzmann brain,
Oh,
statistically speaking.
right. Is this like the monkey and the typewriter thing?
Yes.
Okay.
Yes.
Yeah. Okay. Okay.
Great one, bestie. Yeah, it's the cosmic monkey and a typewriter.
But it might give you a brain, but not necessarily like the rest of the components you need.
I mean, why would you need anything? If you had other things, if you were a full human body out in space, you would die.
Oh. But like in a way that
Although
would
I guess-
adapt.
Maybe given even more time, you could conceivably get a universe that pops into existence a random assortment of particles that's actually a real human person with a spacesuit. But then you'd still starve to death, so... But
Right.
maybe that random particle assortment doesn't need to eat.
Right. It would have
I
like
don't know
adapt to
how
the circumstances.
efficient-
Yeah. Yeah. How the
Well,
evolution.
not even adapt. Not even... No evolution. Just random creation. No evolution.
Oh.
It just pops into existence.
Yeah, I don't think a brain just in space would do very well. Just the brain, you know? So...
That's what you take umbrage with.
Why even go? Why think of it any further? It's like, well, the brain is frozen.
Yeah, so that's
Okay.
how our universe could be cyclical, much like some of my favorite myths, the Hindu mythology cycle where Brahma, the creator, then passes the job to Vishnu, who preserves the universe, who then passes it to Shiva to destroy the universe so that Brahma can create it again. There have been multiple cycles of that. In Norse mythology, we have Ragnarok, but especially in later writings, Ragnarok is the start of a new beginning. After many of the gods and giants and everything die, Odin and Thor's sons survive. 2 humans hide in Yggdrasil, the world tree, in its roots, and they all come out after Ragnarok and start a new world. You see this cyclical theme in indigenous folklore from around the world. You see it in Chinese zodiac. You see it in calendar systems. The Mayan long count calendar had this 5,000 something long year cycle that they would keep track of, and we don't know why.
Right, right. That's where the Mayan 2012 calendar came from, right? Because it was like the last date on that calendar, but that didn't necessarily mean that they didn't just like start a new one.
Right,
It's
exactly.
like they just ran out of space or paper, basically.
Yeah, or they were just, they were like, the next scribe has to do that calculation.
Yeah.
Like, I've done enough.
Yeah.
Yeah. And so I prefer to think of it that way. And I really love that I don't have to choose because, we all know that I don't want to choose. Why choose between a big bounce and a big freeze when apparently a big freeze can just
Eventually
give you
go
a bounce anyway?
Right.
Yeah.
Yeah.
Okay, that's all I had, bestie. What are your thoughts? How are you feeling now?
I mean, I think I feel okay again. But it definitely wrinkles the brain. I don't know how I feel about theoretical physics now or quantum theoretical physics. Because I'm like, I too could just be like, well, I just think that, the particles they just pop in. And then there's another one that comes with it and it just pops out. They just fight it. It just disappears.
There is a lot of math. There is a lot of math that goes with it. Theoretical physics is all math.
Okay.
Even more math than I do as an observational astro person. Yeah, way more math.
Yeah. So maybe I may never understand.
Bestie, I don't.
Great.
I don't understand it. Yeah, you're good.
Okay, good. Because I was just like, sure. It's about as good as any other.
What you just heard is as good an explanation as I can currently give. I don't understand any more than that.
Yeah. Okay.
And that's okay.
That's okay.
Well, it's been a year, folks.
Indeed.
What a year.
Indeed.
This might be the end of this book, but the universe is it's a series. So we're just going to start the first chapter of the next book in the series next week.
Indeed.
No matter what this last chapter has looked like for you, remember you're still space.
Pale Blue Pod is hosted by Dr. Moiya McTier and Connie Gibbs. Moiya created the show with the funny and talented Karine Caputo with help from the Multitude Productions team.
Our theme music is by Evan Johnston, our cover art by Shay McMullen, and our audio editing is handled by the superlative Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Instagram or check out our website, palebluepod.com.
I, Moiya, am Go Astro Mo on all socials.
And I'm at ConStar24 on Instagram.
If you want to support our show, join our community at patreon.com/palebluepod or send this episode to your family and friends group chats.
We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
Thanks for listening to Pale Blue Pod. We'll be back next week.